We're gonna do screen sharing. Turn camera off. Screen share. Okay. Bring this down. So low voltage thermostats. Let's talk about what these switches do down here. So our picture up on the wall there, we have the fan and the cool off heat. Who can tell me what we do, how we're going to set this up if we want the fan to run only when the heating or cooling cycle is going to go? It's going to be an auto, right? Right. Bruce Dickinson in the house. Turning it inside out. All right. I like that idea. Okay. So what is this little devil inside of here? This guy. A bimetal coil, right. Right. Bimetal coil. Okay. Bruce, we were just talking about our old thermostat here, and what we want to know first of all is how can we set this up to get the fan to come on when heating and air conditioning comes on? Without your notes, because you're not having your notes in the test. Yes, that's what we do. How do we get it? Come on when there's a call for heat or a call for cool. We have it connected to the I don't want to run. Yeah, that's what you want. If you want it to be on, if you want it to be in the cooling cycle, you want it to be on cool. But what if you just want the fan? You want the fan to be on all the time. Or cooling, which side would you put the fan button on? Wrong. Auto is going to be where you put it when you want it to come on or off. When the fan, or excuse me, when there's a call for heat or a call for cool, and then that's for the auto when it's called for heat or called for cool. But say you just want to, what my analogy is, that you've got a parking lot in your house and you want to blow the house out, you want to just turn your circulating fan on. Turn the fan into the on button. That's going to run the fan regardless of whether you're getting a call for heat or a call for cool. So it's always going to be on. Okay? All right. Tell me about the fan switch. What do the switches do? Who remembers what the switches do? Chris, what do these switches do?
Like the one that turns the heating and cooling?
Right. Yes, those. What do they do?
Well, they send a call for either heating, cooling, or shut it off. Yep,
that's right. Yep, these are just the selector switch on these older ones to tell which mode you want to be in. That's pretty much the long and short on that. So let me see. What if I said tell me about the bimetal coil? What do you think this is made out of? The coil. This is the mercury. The coil's back behind it. Let me get my pen out here so I can point a little easier. It's a bimetal coil. This is in our reading. Bimetal coil is made of two different types of metal bonded together, right? And they're going to expand or contract due to the heat. And as they expand and contract, they will move this, allowing the mercury to make the circuit inside of the bubble, right? Everybody good with that? Okay. Is that?
What was it made of? What was it made of?
Two dissimilar metals. Yep. Two dissimilar metals bonded together to make a coil that expands or contracts. Okay, well, we pretty much talked most about this so far. What the other day when we did our open up the thermostat experiment, what did we decide can sense the heat on the newer digital guys? What senses the temperature of the thermistor? Right. And what is a thermistor, Lance?
It's
Yeah, that's exactly what it is. How does it do it? It's basically just changing the resistance of the internal part. Yeah, I knew. I could tell. We're just like we're on the same wavelength right there. Yeah, you're right. You're exactly right then, my friend. Okay. Yeah, thermistors, they have a resistance across them, and as the temperature changes, the resistance is going to change with the temperature, allowing voltage to pass at a high rate or voltage to pass at a lower rate. So that's what they're all about. Okay. So let's see. Let me find our digital switch here. Digital, no. We got a digital one up here, but I broke it. All right. Yeah, I wish we had a digital one. I broke the digital one. We can use this though. That's not a good example. All right, let's talk about differences between the old and the new as far as the digital switch. Let me see if we can pull up the next slide here. Okay, this is the one that I wanted to talk to you guys about. Hide. All right, this is the one I wanted to talk to you about, the touch screens. So on this particular guy, on the touch screen, where's the buttons at? Where's the switches? Right here, right? They're actually not physical switches. They're just buttons on the digital display. Yeah, that's what I wanted to say there, is that the difference between the old ones and the new digital ones is there isn't even any buttons. It's all digital now. You don't even have to worry about buttons. You just go in there and click and set up. And that's what you say.
New one breaks too much. Somebody hits the screen too much and you have to replace the damn screen.
Yeah. Yep, that's definitely possible. Definitely possible that your kids are going to cause you problems. So that's the main thing. That's the difference between the new and the old. So the old's got the bimetal strip with the mercury in it, and then the new sensing device is a thermistor, and even the newer from what we got here with the Honeywell stuff, that one's an Emerson. This one actually does have the buttons on it, but the touchscreen up there they're talking about has no buttons at all. So that's the direction of change that those are going in. Okay, go over connections. Oh yeah, connections. Who spent any time with the connections? Anybody remember that? Let's go to page 654 in our book. We went over them a little bit. I put that PowerPoint on the handout if anybody wanted to go through it. This is part of your reading, and there will be this is the matching question right here. This is the matching question on our test, is the connections. There's only 4 that we have to really know, 4 or 5 for the matching one, but it wouldn't be a bad idea for you to spend a minute or two just going over these in your head. But let's pull up. I have them in the PowerPoint that we went through here. Boom. Slideshow from the beginning. Nope, damn it, wrong one. Shoot. Right. Yeah. Right, which ones do you have to know? Let's talk about the most important ones to us. Yep. Something like that might help us. Here we go. R. Power. Everybody remember that red is power? Power from the transformer. All right. Everybody good with that? Chris? Bruce? Nobody heard from Sam, huh? All right.
Oh, yeah.
He said he had something going on today that he would be here.
I remember. I don't remember him saying that. Okay.
I just do.
He said, yeah, it was. Yeah. Oh, yeah. He was asking me
Seems
what
like-
was going on, and
yeah.
he said he had a test.
Seems like now that you say that, I do remember.
Yeah.
Okay. Yep. All right. So the R is this right here. I'll tell you that the page 654. When I ask you what R is, these are the descriptions that it's going to be. Okay. So R is a big one for us. RH, RC, power for those. Those aren't as much of a concern right now. Oh, maybe wait a second. Yes, they are a concern right now. They're pretty important, aren't they? Because it's going to be the switch side of the class 2 power for heating controls and power from let's see, RH is what we're reading. So power from heating only transformer, RH, power from heating only. So we have R meaning power and H meaning heat. And then the opposite of that is going to be RC, our power from our cooling only transformer. That's another pretty important part for us. And then the other one, the other big one that I'm concerned about is, what's the other side of that system right there? The other side of that coil. What do we expect to see? Very good. Common. What's that? What's the letter for common? C. C. Common from the transformer. Absolutely. It's only 3 right there. Let's see. R, RC, RH, C, and then there's one more, so 5, I think. 5 that we have to know.
G.
G, exactly. Yep. G for green, or for G for fan. Yeah. Sorry. Sorry. That is the wire that we're going to use, though, is the green. Yeah. But it's not going to be for ground. It's going to be for fan. So C, W. That might be a big one too. I think I might have a W in there. All for heat from the thermostat. Okay, everybody remember him? W2, W1, the stages. Yep. And then Y. That might be a big one. Call for cooling. Yep. Usually on the yellow wire. And then G. This is our G unit right here. Gangster. This is our gangster wire. I'm not so much concerned about B or O, but I do want to talk about G. G is going to be just energizing the fan relay from the thermostat. So, all right. And the rest of that stuff is available to you if you are interested in learning more about it after we move on. All right. You guys remember going, Steve, you guys had an A on your thermostat. So remember him for these guys?
Yeah.
Yeah. All right. Everybody's fairly good on the connections? All right. That's good. That's your matching question. It's going to be the connections. It's one question worth 5 points, I think. So if you get one right, you'll get one right on the thing too. So we'll get back to our review. Okay. Go over connections from power transformer. All right, connections page. Okay, let's talk about line voltage thermostats. Let me pull up that one. I think that's pretty much the long and short of low voltage thermostats, and I feel pretty confident that you guys have a pretty good grasp on low voltage thermostats. Yeah, see, look at how fun you guys are having right now, flipping around in that book like we talked about the other day. Super fun. All right, let me pull up line voltage thermostats. Yeah. Yep. Yep. Now, some of these questions in here are going to be word for word out of the reading, just so we remember that. Let me start the slideshow from current slide. Okay. So here we have the voltage and current ratings side by side from a line voltage. Yeah, configured setup for the touchscreen on the thermostat, and then current ratings. This to me is low voltage thermostat, and here's the line voltage. Whoop, I don't have my pointer down here. So the one on the left is the low voltage, the one on the right is line voltage, and we remember from our lab that the voltages and currents on the low voltage are going to be very small because they're not actually doing any work. The line voltage stuff right here, we can see that our volt ratings are 120, 208, and 140, or 240, excuse me. And the full load amps is 16 at 120, 9 at 208, and 8 at 240. So that's significantly higher than anything we saw when we were talking about the low voltage guys. And the reason for that is what? Johnny? Yeah, it's fairly common in commercial stuff. Why is there such a higher amperage in current rating, or excuse me, amperage is current. Why is there a higher amperage and voltage rating on a line voltage thermostat than there would ever be on a low voltage thermostat? Current is really what I'm talking about. Voltage is obviously going to be bigger because it's cutting the line side. Right, that's partially right. What I'm getting at here is the reason why on the line voltage side of on a line voltage thermostat, the current has a higher rating is because it has to switch the load of the system. It's actually in line with the load. Remember when we drew the picture on the board? We'll draw it again just so everybody's clear. So, neutral. So a line voltage thermostat is going to be a thermostat in line on the line voltage side. I think that's thermostat in. And then it's going to come down here to the heating element and go up. Remember when we did the figure over here? This was what was this, a 10 amp load? And using our Ohm's law formula, we figured out what the actual, 10 ohms, not 10 amps. This is going to be a heating element down here that has a 10 ohm resistance across there. So we're going to find out what our current is, and V equals I times R, right? It's Ohm's law? I think so. So we've got our voltage, but we're trying to find our current. So we're going to take voltage divided by current. So 120 divided by 10, 12 amps. So let's do it. There's going to be, when this thing closes, when we're closing, there is going to be 12 amps of current flowing through here. Will there ever be 12 amps of current flowing through a low voltage thermostat? Heavens no. You won't have a low voltage thermostat anymore. It'll just be a piece of charred garbage. That's the reason why we have to have such a higher current rating on our line voltage thermostats, is because we're actually switching the working load of whatever we're using. Okay? Remember I was talking about that the other day when we drew this out? Okay. Yep. That might be one worth remembering. All right. Let's see. Let's talk about the actual makeup of line voltage thermostats. So we have the sensing bulb, and then on the sensing bulb of the remote bulb thermostat, it has a volatile liquid inside that as the pressure increases, it's going to go up, push on the, whoop, darn it. I hate when it does that. So, okay. So when we the pressure rises inside the sensing bulb, it goes up and it activates the bellows. Damn it. The pressure's gonna rise in here. It's gonna go through this tube and then it's gonna activate this bellows. And when this bellows activates, it's gonna trip the switch, right? So as the pressure rises, it's gonna move the bellows inside of it, and the bellows, once it gets to a high enough set point, it's gonna trip the switch. Now that's what's the case on the remote bulb thermostat. But the difference between the remote bulb and the capillary tube is that the capillary tube thermostat, let me read what it says. Let me find it. Bulb on the commercial refrigerator placed inside the cooler with a capillary tube run through the thermostat. Who knows anything about capillary tube thermostats? Oh, there it is. That's what I'm looking at. Capillary tube thermostats use a diaphragm mechanism instead of a bellows. That's the difference between the two. I knew I read it in there somewhere. So this guy's got a bellows inside of him. That's going to be right here, and this guy has a diaphragm. Remember? Remember I was talking about that? Yep. Yep. Steve, did you have your pressure switch that you took apart? Samuel Seth Huntington was telling us about it. We'll wait for you to come back. Yeah. But yeah, that's the difference between the two, and I think that was mostly what I wanted to talk about. There wasn't a heck of a lot to talk about on these because they're okay. Talk about switch action. How do they operate? We talked about how they operate. We talked about the switch action from the diaphragm and the bellows. And we talked about why the connections meaning we have to have a larger set of connections in a line voltage thermostat than in a low voltage thermostat, just because of the amount of current that we're passing through there. It's going to be a lot greater. Okay. Talks about types, cap tube. All right. I think that's about all we had to say about remote bulb thermostat, or excuse me, dang, why am I having such a hard time today? Line voltage thermostats. Find it? Cool. This is what the inside of the pressure switch looks like, fellas. As the pressure rises from here, you can move this around, up and down, and then that's probably you take the diaphragm out. Yeah. Right there. So as the pressure increases, it's going to move this toward the switch in here, and then once it gets high enough, it'll get a switch being made inside of there. Once the pressure gets high enough, it'll turn that off. This is up and dry. What it looks like. You can hang on to the spring. Is everybody looking at this? Everybody seen this in their hands? No? Yes? Okay, check it out. It's neat. Yeah, don't get Jonas germs. Okay, that's a great segue into pressure switch. Great segue into pressure switches. Okay, what is a pressure switch? Bruce? Pressure switch is when it's pressure. Yep, it's just that simple. It's a switch that's being controlled by the pressure of the system. That's exactly what it is. Nice job. Pressure switch. So we have two different kinds of pressure switches. We have the pressure switch like we have right there that's an unsettable one. It's just, man, once it gets to this PSI, it's going to pop. And it doesn't care what what it's going to happen. That's kind of, I would consider that a dump pressure switch. And then you have what we looked at, these guys over here on the wall, right here with the adjustments. These are the ones that are a little bit smarter. You can adjust them for your cut in, your cut out. These are what I would call the smart pressure switch, and I'd call that one the dumb one. In and out. What would be a common scenario that we would see a dumb pressure switch apart from what we got out there? There was one specifically in the book that I'm talking about in the reading. Air conditioner. Remember that? Remember us reading about that? Where there's the air conditioner just has just a dumb pressure switch on the condensing coils. That if the pressure gets too high, it's probably right in line with the condenser. So the power for the condenser is going to go through this pressure switch. Let's probably do it like this. So the pressure switch that we're going to have on that is going to open whenever the pressure gets too high. So it's going to be closed, and it's going to be one of these guys, right? Is that a pressure switch or a flow switch? Flag?
D.
The D. Okay, yep, the D. You're right. You're right. The pressure rises, which is going to open. So this will be in line with our compressor motor on the air conditioner. So as the pressure rises, that's going to open and it's going to kill the compressor so we don't overload and burst that circuit with pressure, burst the plumbing circuit with pressure. Okay. We want to see a picture of it. Can pull it up. Let me pull it up just so we're the exact words that they say and you can hear. Yep, I'm just following right along with what we got in the book. So if you see it in the reading, it's right there. What are we in? 35. DDLP 2 pressure switches, KPC. Slideshow, current slide. Oh my goodness, PowerPoint has stopped working. There we go. Oh. Yeah, we didn't pay the PowerPoint bill. I probably ran through all of our PowerPoint minutes. Damn it. All right, here's what I wanted to see. Here's one with the pressure switch attached right to the system, right to the pipe there on the left. And then you have a capillary tube on the right that's allowing you to move further away from where the actual system is. There's your adjustable guys. Adjustable pressure switches allow adjustments to the operating point of the differential. The adjustable switches are also used in refrigeration. Close on rise switches. Let me scroll down on my notes. Close on rise switches have an adjustment for the cut in and the differential. The cutout is set. Yeah, I don't think I need to read that. No, pretty sure there's nothing there. Here's your air conditioner. High pressure switch on your air conditioner. Booyah. Air conditioning systems typically have a small fixed pressure switch connected directly to the system. All right. Your summary. There's our lab. Remember him? Remember that failure of a lab? Yeah. Steve, did you ever hear back from your guy?
Yeah.
What did they tell us? Yeah, you're the only guy that heard back, I think. You finally heard back. What'd they tell us?
I can't help you in the class, but if you want to order something.
Did you reply, kiss my butt? Yeah.
Alright. It's rated at 20-inch WC, wire terminals, one of those places. There's no voltage or amperage rating, and formula. That's all that.
Okay, well, at least we got a reply. That's cool. It isn't really that helpful to what we were doing, but at least somebody came back at us. So yeah, that apologize for not having some great pressure switches there for you guys to put your hands on, but you know, the reality of that situation is exactly what we had. You get called to a furnace somewhere and you suspect the pressure switch is gone, man, you got to jumper that thing out. If your system starts to run and after your pressure switch is gone, the reality is you got to order a new one. You know? So okay. Let me make sure we covered everything that I had in my notes about pressure switches. Okay, pressure switches, what are they? Mention air conditioners, what are they for? Everybody good on those? What they are and what they're for? Me too. Okay. Now let's talk about resistors. This is where you guys who missed the other day may want to pay attention. Let me find where our spot is. This is actually in your book. It wasn't included in the reading, but I promise there's not a lot of questions on it, and I'll tell you exactly what you need to know right now. All right, there we go. So the resistor. These guys are a device having resistance to the passage of electric current. Resistors are commonly found throughout the HVAC industry. You will most likely see them on your circuit boards. Its measurement is the ohm, and they're commonly used to limit current in a circuit. Now, we see here we have the color code. Talked about this the other day, guys who were here, but the guys that weren't, we have, let me get one out. No, I want you to just know what it's for. I'm not asking you to memorize it, just what it's for. You go check that little guy out. Bruce, you weren't here? Check him out. And Stevie. Probably seen these, but this is an example there. It's got a color code on it. We have these guys right here. So on this particular one, this is the first digit, the second digit, the multiplier, and the tolerance. So what it means by this is it means that the first digit is going to be brown. So we go over here to our chart. It's going to be 1. Second digit is green. It's going to be 5. So those are our first 2 digits on this guy, 1 and 5. And then this is our multiplier. And I believe that's in the 100. What color is red? Red times 100. So that's going to give us a 15K value on our resistor. 1, 5, K. Whoop, geez, maybe draw a K, guy. Trying to draw the ohms first. K, ohm, resistor. And the final part here, this purple guy, most of them, I can't say that I've ever seen the purple. Most of the ones that I've ever seen have been gold or silver on this final band. And that's your plus or minus percentage. So on this guy, our tolerance for, if we were to hook this resistor up to our meter and check it out, the tolerance is what, plus or minus 5? What do we got? 0.1. So that's the amount of tolerance that we get to have on this resistor, is that it's going to be 15K plus or minus 1%. So we can have 15.1
0.00 whatever 1% 15 is. 15K. So it's going to be fairly accurate, but not super accurate. So if we're that's all the color code is it's a way for us to be able to look. If we remember at this, be able to look at a resistor and identify what the value is. Okay, that's what I want you guys to take away from this. So, what color you got there, Steve? Get your reading glasses out.
I need some.
Sure. Brown, red, and yellow. So 15 with a red plus or minus 2, or excuse me, 15, 1, 5, and then red is our multiplier, so 100, so 15K plus or minus, what was your last one? Yellow. Yellow or gold? Probably gold. Is there 5 on there? 5 bands?
Too small for me to see.
Sure. Okay. All right. We don't need to get hung up on that because everybody, when they get to the field, is going to have the meter, and they can just check out the resistance. But I did want you guys to know that you can figure that out just by reading the color code. So the resistor color code is for sizing resistors. All right. Now we're going to talk about a diode. Diode is a semiconductor device with 2 terminals, typically allowing the flow of current one direction only. One direction only. Diodes are often used to control the direction of current flow in circuits. Also commonly found in HVACR circuit boards. Diodes are used to convert AC voltage to DC voltage in what's called a rectifier. There's a diode in here for you guys to see too, I think. There was one in here the other day, but we had some people playing with the toy box. This is a diode right here, buddy. It's very similar to a resistor, but the black and the gray are what are going to see a difference. So, okay, there's the symbol. You'll learn a little bit more about those symbols moving on. I put any questions in here about an SCR, but an SCR is very similar to a diode in the fact that it conducts in one direction. An SCR has what is known as a gate, and it acts similar to an electronic switch. So we can use this gate to open and close the switch to allow current to flow in one direction. These are used in the conversion of AC voltage to DC voltage and what it's called a converter or an inverter. Okay, transformers. Here's where we spend a little time. Transformers. We can see here that the primary on this transformer on the left has more windings, and therefore and a higher voltage, and the secondary side has less windings and a lower voltage. So that is called a what kind of transformer? Step down transformer. Absolutely. Absolutely. Exactly. Yep. They're not as efficient. So if we were to juice up this secondary on this particular guy with 24 volts, we probably wouldn't see a real solid 120 on the other side. Step up transformers, especially when we're talking about real small ones, aren't very efficient. They don't pass the voltage through very well. We could do that though and check it out, see what it's like if we wanted to. Okay, let me see where we're at on track here. So resistors, talk about color band. Diodes, what do they do? Bruce, what does a diode do? It allows current flow one direction. Yep. Allows current flow in one direction. Pretty much. It blocks it. It allows it to flow through one way and it blocks it the other way. So if it's trying to, if the diode, let me draw it up here. Diode is got, let's see.
AC to DC.
Yep, it's used for that. Yep, it's used for, that's a very common place, is in a rectifier. If we wanted to, on your low voltage side of your transformer, when you're converting 120 to 24, and then you needed a DC part, DC 24. You could put a rectifier in, and it would be 4 diodes in kind of this diamond looking shape. We could talk about that all day long, but we got to test it. So,
It's on the right side, right? On that side. So the current is going to be allowed to flow through here, and it's going to not be allowed to flow through here.
what did we say? Somebody said something about current flow. Something I didn't hear what was said there about the diode.
Oh, no, that's just saying the anode's on the right side, or the side where the timer goes.
Right there.
Yeah.
Anode is here. Cathode is here.
So does it do both functions, or can it be either or?
So it blocks one direction, and it allows it to path in the other. It allows it to flow through in the other. So yes, it does both things at the same time. So current can flow through this way, but it can't that way. So that's what I'm meaning about directional. It can only,
Like it does that and converts it to AC.
No,
DC,
no.
Or it can just be that or.
so it's not individually going to convert AC to DC. There has to be more in the circuit than just that. But that's a common use that you will find diodes in as a converter or rectifier. Yep. And we did, let's see, did we see some stuff in? Seems like I'm doing symbols with the second year guys right now. And it seems like I saw us have some symbols in there of a rectifier on one of the things that we were looking at the other day. So we'll get to that, I promise you. Okay. Transformers was where we left and went back. Let me check my notes here. Are you guys feeling pretty confident about a transformer? Talk about what they are and what they're used for. What are transformers rated in? Volt amps. Yes, sir. That's exactly right. Volt amps. Sometimes in our industry, in your guys' industry, I've heard Charlie call them watt. Well, what is a watt? A watt is a measurement for power, right? So power equals voltage times amperage. So what is a watt? Watt equals volt A. Volt amp. Same thing, just different ways of saying it. Okay. And then this is kind of a little bit of a strange segue that my man Ken had going on here. We go from talking about transformers into talking about relays. So, or I guess we're going to review low voltage thermostats real quick, but we don't need to. Let me find where he wanted to start talking about relays. Come on. There they are. Okay. A relay is an automatic switch that requires some method for opening and closing. This is often accomplished through the use of a relay. A relay is an electronically operated switch that uses an electromagnet to open or close a set of contacts. Okay? Everybody good with that? Knowing what a relay is? What's the difference between a relay and a contactor? A relay is going to be used for the switching side of things. It's going to be used as a switch. A contactor is going to be used to control the load, right? We see the contactors on motors, heating elements, big loads. A switch, like a relay could be considered off of like maybe a thermostat. Okay, something that's gonna deal with the signal side of things. Yes, sir. Yeah, it could be. Yep. Or it could even be in line with like a pressure switch, something that's going to not have a load on it. Is basically where you're going to see a relay. Their terminals are smaller. We all looked at the terminals; they're much smaller than the contactor, and that we can just know by looking at that that's not going to take a huge amount of current to pull that thing out of the water. So that they're typically used on the switching side of things, especially the little ice cube relays that we handed out.
That's the big difference between the two. Here's how they work. Did we not move? Did we move or did we not move? We didn't move. There we go. Here's how we work. We apply a voltage to the coil down here. This is an electromagnet right here. We apply a voltage to this coil from a switch or something like that. It's going to apply the voltage. This is going to create magnetism. It's going to pull this armature toward the magnet. And by doing that, it's going to move this from the pivot point. It's going to move this device up. And it's going to open these contacts. This would be what kind of contacts right here? Those are normally closed. Yep. It's going to move them, open them up, and it's going to make these contacts, which are very good. Very good. When we are talking about contacts on a relay, what state are they always going to be in when we're talking about them? Like if I say normally closed contacts, they're going to change whenever the contactor is energized. Yes, sir. When we're talking about them, they're always going to be in the de-energized spot. So a normally open set of contacts, when we're talking about it, is going to be in a de-energized spot. So normally open is going to close when we energize the coil. Right? Right. Okay. Okie dokie. And here's some more stuff about how the relay works. Or yeah, the relay works. Sorry. Should have brought my clicker down. Okay. So here's some examples of they're calling these a fan. Something in here is called a fan relay. It must be A. The fan must be a small, maybe like an induction fan, something that's going to move the gas around in there. Might be small enough to be on a relay. But then we're talking about the three-phase contactor for your compressor motor, single pole contactor here for a high load, maybe a heating element. Here's a motor starter. We passed them around the other day. And then large ampere systems may use multiple contactors. You'll see those out in the lab. Relays and contactors and starters all have contacts that open and close to complete or disconnect a circuit. Ice cube relay on the side there. Contacts for control relays are often small. This is because they do not need to be connected to the load current, since they are only relaying the signal. Repeating myself. Typically, relay contacts are rated for 15 amps less. Contactors that are connected to the load will need to be larger. So we can tell easily right here just by glancing at these two. This is going to be on a much bigger load than this. Although they operate almost the same, with this having the exception of having overloads that we'll talk about in a second. They are almost identically the same thing. It's just one set up to switch a much higher load. Okay. There's the operation of the contactor right there. Everybody pretty solid on that. When we energize, we create the magnetic field that pulls the plunger down. Okay. All of these things work on the same principle. Here's a manual overload reset. This is just a picture of one. This looks to be like if it were to be in line with a coil inside of the motor somewhere. You'll see that pop out if the coil gets too hot. You'll have a manual reset on it. That's very similar to this, where you have the manual reset. The bimetal coil that's inside of here gets too hot, it'll trip this, and you'll have to push that back in to reset it, manual reset. Okay. These guys are they're kind of like overloads, but more this one on the left, the thermal overload used to protect electric strip heaters, that's more of a switch. They call it an overload, but I would think that of being just a temperature switch.
those are commonly called a clicks-on in the industry. I've seen a lot of them before. And the bimetal current overload used for small hermetic compressors. There's that guy. And then there's an overload block on the bottom of that motor starter on the right of the screen there. Pilot duty overload relay. Magnetic overload relay is another type of pilot duty overload. The advantage of this type of overload is their ambient temperatures, thereby avoiding nuisance trips. Okay. Okay, relays, what are they used for? No load on the switching side. Switches are in the de-energized spot. Contactors are used for opening and closing larger loads, and the contacts on the contactor are going to be greater, larger than on a relay. And then the last thing that I had to talk about was transformers, and we already kind of breezed through those. Talk about what they're used for. They're used to transform voltage from one voltage to another voltage, and they're rated in volt amps. Okay. I feel like if you heard what we said and remember kind of what we just talked about, you're going to probably do A-okay on this test. So you guys are familiar with, let's see, what do we got? We got about an hour to take the test. If you want to take a pee break real quick, go ahead. There's 36 questions. I'll pull up how to get to it when you guys get back in here. Okay. You all right?
No, just kidney stuff. I had a kidney transplant about almost 7 years ago now. So.
Just making sure you're on the up and up.
Yeah, I go in every 3 months.
Sure. Just get a workout.
Blood work and go see my kidney doctor. Sure. I got doctors in Sioux Falls and Rapid.
All over the world. Yeah, I gotta do something similar. I have a condition with my blood called hemochromatosis that doesn't allow me to process iron very well.
Oh, really?
Yeah, so I have to go get my blood taken every couple of weeks or months and make sure that my levels are all the same. I had to do what's called a phlebotomy. I had to do they take a pint of blood out every week, and I had to do about 16 of them in a row just to get my levels back down.
Yes, that's it. Because my blood was so thick, I was on blood thinners, and I was still getting a bunch of blood clots. So they just bleed me. You know, they just take out a big old bag and every so often.
Yep. No fun, is it?
No, it's not. I mean, it's just.
You feel like dog shit when you leave because you're like.
Right. Yeah, it's not so bad now. They got all dialed in, but like right after the transplant, man, I was in and out. You know, I take so much medicine, and then they had to regulate. You know, like it's hard to get like magnesium.
Yeah.
And because it comes from like greens and stuff like that. And I mean, you just can't eat enough.
Yep.
Of that shit. So I take a lot of magnesium supplement. Well, I was having trouble with it, and they were trying to get out of doses and stuff. So I go in like every week to go get like
Sure.
magnesium drip.
Oof.
So after 3 hours, like freaking big.
Yuck.
So, yeah, that's what I was doing this morning.
Okay.
Blood. I was there at 8 o'clock. Figured, I usually go down to like the clinic and start just there. Usually, I just walk in and that food's going around so bad, and it was just packed.
Sure. Why don't I see what I'm wanting to see?
That's the stuff that
All right, there we go.
Is that when? Or yesterday, tomorrow? Yeah, today. Good tomorrow. Good, George. Yeah. Usually lasts about half an hour, but $100. 130, I think. It's 100, so.
Okay, guys, everybody back? I can run out to the library. That's what I get that when you guys do it. Or is that something that you're gonna be able to get? Or are we gonna just plan on doing it in the library?
I guess the library.
Okay. Okay, guys. This is the spot right here. These stats, pressure switches, and relay stats. You can start. Yep, just hang around, we'll talk about it.
I'll just go to the library, log on, and then.
Yeah, I'll go up there with you. Everybody good? Got me right back down.
Probably have to leave my phone in my bag.
Are you trying to cheat? Can I trust you?
I'm gonna get my hand.
I expect you to not cheat.
Okay.
I didn't stay for lunch. What they have?
Starts with a 9.
Want to go?
Mhm.
All right.